Okay, moving on in our look at section 2, casting and molding. We're at the second chapter in that section, chapter 5, which is looking at casting metals using expendable mold techniques. Okay, so expendable mold techniques or expendable molds are basically molds that you're going to build, create for the purpose of that casting, that single casting, and then the molds are going to be destroyed when you get the part out of that mold. Okay, so after the part has cooled and solidified, you have to destroy the mold in order to get the part out. And then if you want to make another part, then you have to remake the mold. Okay, so these are expendable mold techniques. Now, if we look at a big picture view of casting methods, this is for metals and plastics and other materials as well, ceramics. Okay, we can break the casting methods down into two large groups, basically expendable molds and permanent molds, right? And this is chapter 5 where we're at right now. This will be chapter 6. Okay, and then breaking this further down and under expendable molds, we have permanent patterns and expendable patterns. Okay. And we'll talk a little bit about patterns. Patterns are different than molds, right? Patterns are what we create the mold around. Okay. And so we can have a permanent pattern, which is kind of the more common method here, or an expendable pattern. That is, the pattern is also destroyed when we're making the casting itself. Okay. Most of the metal casting is going to be dealing with permanent pattern, and here we can have the green sand mold casting, high pressure mold, all these kinds of castings down here. Investment casting is more in the expendable pattern configuration, where the pattern is actually going to be burned out or melted out prior to the solidification or prior to the introduction of the molten metal and its solidification. So we'll look at both of those in this analysis here. The what I've highlighted in green are the types of expendable mold casting that is illustrated in the textbook. Okay, we're going to look at the green sand or sand mold casting and investment casting in this presentation. Those are the main players here, as I said, in this area here. All right, so first we're going to look at sand casting. So this is probably what you think of the most when you think of casting metal. Okay, this is the oldest technique for casting, where we create a mold out of sand. Okay, so silica sand is used with a bonding agent to form the mold, right? The bonding agent is just going to hold it together so that it doesn't just break apart easily. So it's kind of like a sticky sand or a sand that holds its shape very well. It's suited for low production volumes or prototyping, right? So it takes time to make the mold because you have to build it around the pattern. So you have to make the mold. You have to make sure it looks good. You have to do some pre-processing of that mold. Oftentimes that includes identifying where the gates and runners are going to be, creating the sprue and the risers and all that stuff. So it is time consuming. And afterwards, you are going to be breaking the mold apart. You're going to be destroying it, breaking up the sand. So even though the sand is reusable, you can reuse it a number of times. You still have to break it apart and all that stuff. So it is a time consuming process, and that's why it's suited for low volume production. The pros of sand casting, well, it's very low cost. I mean, sand doesn't cost anything. You can get it pretty much anywhere. So it's low cost. It's a very simple process, owing to the fact that it's one of the older processes known to man. You have very cheap mold material. Like I said, sand is pretty much everywhere you look. There's a wide range of product sizes, from small to large products, okay? And it uses all common casting metals, so you can use it with just about any casting metal. The cons of this sand casting method, well, it has low tolerances, poor tolerances, right? It also has rough surface quality, right? The surface is going to be, the surface of the casting is going to be derived from the surface of the sand that it's resting up against while it's solidifying. And so sand is not going to be smooth. Sand is not going to be, what you're going to want for a very straight, planar, very accurate surface. So there is going to be, generally speaking, lots of post-processing necessary with a sand casting, such as drilling out the holes, reaming the holes, redoing the surfaces, machining the surfaces to make them smooth. Sand molds are fragile, although with the introduction of the bonding agent, they're not, I mean, you can't drop it, right? But it's strong enough so that it is not going to just fall apart. You need to use low filling speeds and pressures, right? Because if you're pouring in this molten metal at a very high speed, you're actually going to get tear outs of the sand. So you're going to actually pull and mar the sand molds. And molds are poor heat conductors. Basically what that means is after you pour in the metal and while you're waiting for it to solidify, it's going to take a long time for it to solidify, right? It doesn't conduct heat out, which you might think is a good thing, but it does mean that you're going to have an extended period of time where you're waiting for it to cool so that you can then move on to break it out of the mold. Okay, so those are the pros and cons of sand casting. The methods for sand casting, we already looked at a illustration like this, so let me just kind of refresh this for you. Remember the mold is made up of two parts, right? We have the upper part, which is called the cope, and the lower part, which is called the drag. And you can remember that the lower part is the drag because the D for drag also stands for down. So drag down, the D is down, and cope is on the top part, all right? What separates the cope from the drag is called the parting plane, right? And you can see here the parting plane is going to not perfectly bisect, but result in an upper half and a lower half of the part. Typically speaking, on a cast part, you can see where that parting plane is. If you find a cast part, cast in metal or even plastic, if it's done using this upper and lower type of mold, you can see a line going around the perimeter of the object, and that will be where the parting plane is. Okay. The sprue is where we pour in the molten metal, right? So the molten metal comes in here. Usually you have a reservoir here that houses extra material, liquid material. And you also have a runner, which is also going to allow for overfill, right? So that takes into account when the shrinkage occurs, right? When it shrinks due to cooling, we want extra material here to be taken up, right? The only other thing here that we need to talk about is the core. The core is used to make hollows, hollow shapes, hollow geometry in the casting, and then the gate is what we call the shape of the area that the metal is going to flow into the part, and that's going to be removed afterwards. Okay. Another way to look at this, and this shows kind of the steps. The first step is we're going to take, let me back up a second. So when you're doing a sand casting like this, what you do is you start with a pattern. The pattern is going to be the object that you want to cast. Okay. The pattern is going to be sized up slightly, right? So if you want to cast an object that's maybe 6 inches by 1 inch by 5 inches, you're going to calculate how much you need to size that up based on the material that you're using, and you may end up making it 6 1/4 inches long and 5 1/8 inches long or wide. Okay, so the pattern is going to be slightly larger than the finished object because we want to account for contraction. Okay, remember, contraction is when the part shrinks a little bit. Shrinkage is when the metal solidifies, it's cooling, and the the metal is drawn down from the risers and the sprue. Okay. Now we take our pattern and we split it in two. We cut it in two, and we cut it along where it's going to sit on the parting plane. So step number one here, we take the lower half of the part, and we put it on what's called a half pattern plate, right? So this is just a piece of wood, right? You'll see it in the videos, so please watch the videos that I gave you. But you put it down on the top of a piece of wood, and then you put the box around it. The box is what the drag is, or where the drag is, right? The box is the drag. And then you fill that box with sand, right? And you pack it in there really good. So the sand is around this half pattern, right? And then you level it off, okay? Remember, the sand is going to stick together, right? And then you flip the drag over. So now the drag is in its proper location, right? You flipped it upside down here. And you're going to put the cope on top of that. All right? So you put the cope on top of it. The cope is just another box. Right? You put the cope right on top. See these alignment pins right here. And then you're going to place the top half of the pattern up there. And usually when you split the pattern into two halves, you're going to have pins that help you locate it, right? So that way you can accurately locate the top half of the pattern and the lower half of the pattern. So you put the top half of the pattern on there. You put in the sprue pins and risers, right? So you go ahead and place those in there. And then you fill this with sand. You fill it with sand and you pack it in again so it's very, compact and there's nothing loose. There's no gaps or anything. And then you take them apart, right? So you take the cope and the drag and you take them apart. And then after you take them apart, you take the half patterns back out again. And you also take the sprue pins and the filler pins or the riser pins back out again. So you take all that out and then you reassemble the cope and the drag. And what you end up with is a cope and a drag with a large void right there where the pattern was. And that's where you're going to pour your liquid metal. And you pour the liquid metal, you have your vents and your riser and all that good stuff. And then the result is your finished part. Right? So that's the steps 1, 2, 3, 4, 5, 6. Kind of, there's probably like 7 or 8 more in there that I kind of went through, but they're not showing in here. So these are the 6 major steps. Okay? And again, please watch the videos because I have several videos that are really neat videos where you can see them actually doing that, both in a production operation and in like a backyard kind of thing. Okay, so it's really neat, really neat. All right, so moving on to the other type of expendable mold, major type of expendable mold, is investment casting. Okay, investment casting, this is one of those where we have an expendable pattern, right? So let's go back here. This pattern is going to be saved, right? This pattern is typically made out of wood. It could be even 3D printed. It could even be made out of metal if you want that, all right? But this pattern right here is going to be saved, right? So we're not going to destroy that pattern. We use it to pack the sand, and then when we take the cope and drag back apart again, we take the pattern and take it away, and then before we reassemble the cope and the drag here. Here with investment casting, the casting pattern is going to be made out of wax, and we're going to burn the wax out or melt the wax out before we then pour the liquid metal back in. All right. Again, I have a beautiful video for you to watch for this. It is very informative. It's very cool. So please watch the video so you fully understand what's going on here. Investment casting can be used for high and low volume production. I think one of the videos I have in there, you can see a robotic arm that is helping to create the investment casting. So as long as robots are involved, you're talking about high production, or at least relatively high production. Okay. It can create highly detailed parts, right? The wax here, right? And the object, what you're going to use for the pattern, the mold is going to be plaster. And so that's a much smoother surface, and the wax can be finely detailed. So you can have much higher detail. You can have closer tolerances. You can have thin-walled structures. Draft angles and parting planes are not required, right? The downside is it's expensive, right? Because now you're consuming the pattern as well as the mold. And so, you have to kind of go through the whole thing again, all right? It's very time consuming, and the solidification and cooling is very slow. All right. So how does the investment casting work? Well, you start with the wax patterns here. Okay. So all of these objects, these 6 objects right here, are the wax patterns. These are perfect replications of the object that you want to cast or create as a casting, right? They still need to be sized up slightly because we still have to deal with contraction. We can't get away from metal contracting slightly. So we have to size everything up by a small percentage so that when it contracts, we have a known, or we have a size that we want. Okay. Then what the wax patterns are stuck to is your gating, what you call your runners and gates here. And then this is the sprue, right? So this is where we pour in the metal. Now it kind of looks weird because what you're looking at is going to be the negative shape. What we're creating is the part that we're going to then fill with metal. All right. So we have the gate system here, we have the sprue, and then we have the parts. And this is all made out of wax, Then what we do is we take this and we dip it over and over again in what's called a ceramic slurry. Basically, like it's a plaster type ceramic slurry. And the slurry is going to stick to the pattern, right? So you dip it over and over again. And basically, you want to create this hard ceramic shell. Think of making an M&M, a peanut M&M, right? So this is our peanut right there. And we want to coat it in a hard coating of chocolate. So we're going to dip it not once, not twice, but over and over and over again to build up that shell of chocolate. And that's what we're doing here. We're dipping it over and over again in the ceramic slurry to build up that coating. So now what we have is we have a wax pattern with a wax gating system that's covered in this hard ceramic slurry. All right. So a hard shell. Then we're going to, what they're missing here. Okay. What they're missing here is the step in between the shell making and the investment casting is where you take this part right here, this whole thing that you just made, and you put it in an oven upside down and you melt the wax out. So upside down means all the wax is going to flow out of the sprue area right here, upside down, right? So you put it in an oven, all that wax melts out upside down, and what you're left with is an empty, a hollow ceramic shell. And then you pour your molten metal inside, let it cool, and boom. And then you break off the ceramic slurry, the ceramic shell, and you have your finished part. All right. So that's investment casting. Again, please watch the video. There's a couple of videos on this. It's very cool. And actually, let me back up. I remember I said in the orientation, our kickoff meeting, that I have other videos in the YouTube channel for this class, in the MDT 201 playlist. So if you want to see more videos, if you still need a couple more videos to kind of, answer some questions you have, please check those out, because there's some other videos in there that are really neat and will help to illustrate what I'm talking about here. All right. So the last thing that we're going to talk about here is design guidelines. Okay. Design guidelines for expendable mold parts. And we talked about this at the end of the last presentation, chapter 4. But it bears repeating. We want to maintain constant wall thickness, right? Changing wall thickness is going to have problems with, remember that thin-walled sections are going to solidify faster than thick-walled sections. So if you have thin and thick walls in your part, as you're pouring in the liquid metal, as it's solidifying, the thin sections are going to solidify first, and they may cause problems for the thick sections. Remember that as molten metal solidifies, it contracts, it shrinks, right? And so that shrinking is going to pull metal from other areas. So that may create porosities or inclusions, holes basically in your part. We want to radius all corners. We want to design the junctions, walls coming together very carefully. Okay. Substantial design guidelines exist between each casting metal, right? Between casting steel and iron, and between casting steel and aluminum, and iron and aluminum. All of those have different guidelines, different requirements, different constraints. Okay. So that is chapter 5. Okay. Again, please watch the videos. They will help you to understand what's going on. And I will see you in the next chapter, chapter 6, where we look at permanent mold castings.